Hello everyone, welcome back to LabTube. In this video I'm going to do question 22 of section 16.7. The question asks to evaluate the surface integral of a vector field. The vector field which is given here, xi, yj and xz over the helicoid given by this curve, this function, this vector function, and it is oriented upward. So note that unlike the surface integral for functions, in the surface integral for vector field, you should have an orientation fixed. In this case, the orientation, the question says you have to take the upward orientation. Okay, what is that? We will discuss about it and we'll see how does it work. Okay, so in this case, I want to evaluate this line surface integral for vector field. Okay. So if you have that case, you have to have an orientation. So let n be the orientation for S. What is an orientation? Orientation is a continuous function of vectors over the surface which are unique, which are perpendicular to the plane, and it is continuous. So those are the conditions for that. If I have that given explicitly, then I dot product my vector field to n, get a function. Then when I have that function, then I can integrate that function over that surface. So it's surface integral of a function. But in most of the cases, we are not going to have such an orientation. We are not going to have an orientation given explicitly. So to do questions like this, what we need, instead of having an orientation explicitly given, is actually this parametrization. That's the only thing we need. And if I have a parametrization which has the same orientation as mentioned in the question, what does it mean? If I have the parametrization, I find Ru cross Rv, it is equal to n, or it specifies the orientation asked in the question. If it is upward, then you don't need to go to surface integral of a function. You can go straight to a double integral. Find Ru, find Rv, cross product, you get a function. Then dot product that function to your vector field, you get a function, and then evaluate with respect, integrate with respect to u and v. Okay? So let's see what is Ru cross Rv, and we have to check that it is an upward orientation. So let's see. Ru here is given by cosine v sine v 0. Rv is minus u sine v, u cosine v, and 1. Okay, that's that. I can cross product these two. The cross product, since I have written in a nice way, so I can see cross product. The first component is sine v. The second component is minus sine, this times that, minus cosine v. And the last one is u cosine v times cosine v. So it is u cosine squared v minus negative u sine v times sine v, which is u plus u sine squared. I can factor out u and I get this. Okay, that's the cross product. Okay, we know cosine squared plus sine squared is equal to 1. Let me just raise that and write u. So now at this point you have to stop for a moment and ask yourself, is RU cross RV, the orientation given by the parametrization, upward is it upward or downward? You have to check that. You have to decide that if this is equal to the orientation that you're looking for. Okay, how I can check that something is upward or downward? Here is how you can check. In these specific cases, look at the last component. And if it is positive, it means it's upward. So, see, it is u. U in the 0, 1, u is positive, so the third component is positive. That means it's going to be upward. This is not always true, but in this kind of examples, or the examples which are related to our book, this is always true. Just check the last one. If you want to check if it is upward or downward. If it is positive, it is going to be upward. If it is negative, it's going to be downward. Okay, so that's upward, and then we can use this formula here. Okay, so I have integral of f ds. Okay, the steps I have to take here are these. So find the region. What is the region here? Region is given actually in terms of u and v. It is d. So I have double integral over the region of uv. F, I didn't write here, but plug in your variables in f. So u and v in f. Then dot product it to RU cross RVs, which is sine v minus cosine v u. And then you'll get a function. Yes, it is going to be a function in uv, and then you can double it, find the double integral with respect to those u. Okay, let me simplify this. Region going from 0 to 1, 0 to pi. Plug in your parameters in your function. What does it mean? It means that for z, you plug in v. So I have v. For y, you plug in u sine v. And for x, you plug in u cosine v. That's my vector field written in these parameters. Dot producted to sine v minus cosine v u du dv. Okay, if I dot product, I'm going to get a function in uv. So uv times sine v, there is some, yes, okay. V, so it's v sine v. This guy here is minus u sine v cosine v. And this guy here is plus u squared cosine v du dv. I have to integrate with respect to u first and then with respect to v. So let's integrate with respect to u. So here, I have no u here, so it's going to uv sine v minus, this is going to be u squared over 2 sine v cosine v plus, this is going to be u cubed over 3 cosine v going from 0 to 1 dv. Okay, now I have to plug in 1 here. So the result is going to be v sine v minus half of sine v cosine v. And this is plus 1/3 of cosine v. Minus, plug in 0 for u, this will be 0, this will be 0, this will be 0, there will be nothing there. So this is d. Okay? So I have to evaluate each part of this thing. So antiderivative of these functions for, let me write it here now, I can write it here. To evaluate this one, you have to use integration by parts, and you can get like this. So it is d minus cosine v, and it is equal to minus v cosine v minus negative integral of cosine v dv, which gives us cosine v, antiderivative of cosine v is sine v. Okay, so that's the antiderivative of first part. Antiderivative of negative half of sine v cosine v dv. This is, you can take, use substitution. This is the function. If this is the function, sine v is the function, its derivative is cosine v. So basically we have u dv, u dv. So u du, sorry. Then it is going to be integral of sine squared v. But I need to put a half there because it's antiderivative of u. And then there's another 2 there, so it is minus 1 over 4. There's minus. So that's antiderivative of that part. And then antiderivative of the last part, which is the easy part, is 1/3 of sine v. That's great. Now, all of them going from 0 to pi, 0 to pi, 0 to pi, and then evaluate them. Evaluate them. So here, if I evaluate for v sine v 0 pi, I'm going to get 0. But for cosine, I'm going to get minus pi. Cosine of pi is negative 1, so that's it. Minus 0 here, so it's 0. This one, plug in pi, you get 0. Plug in pi and 0, you get 0. So the value you get from these things is only this part, which is equal to pi. Okay, very quick wrap up is that when you want to evaluate a vector field, integral of a vector field over a surface, or surface integral of a vector field, you can either do this, but this is not practical for us at this moment, but it works well when you have a parameterization, and the parameterization, the orientation given by that parameterization is a nice orientation. Okay, then in that case, you can plug in values in function parameters in your vector field, then find RU cross RV, dot product, and we get a function integrated with respect to U and V. We did that, and we turned our surface integral of vector field to an iterated integral of a just regular function. Iterated integral, find the inner one, find outer one, and that's the value for this surface integral. Thank you for watching this video.